Hello guys, in this video we'll see what is a metric space. Okay, so first let us see the motivation. Why do we need metric spaces, right? So consider the following equations. Say we have equation x plus y is equal to 1, which is this equation over here. Okay, so we are in 2D now. Okay, and then we have this equation, that is x minus y is equal to 0. Okay, then we have one more equation, that is x is equal to 1. So basically this is 0 y. Okay, now what I want to do is I want to solve for x and y, okay, such that all these equations satisfy. Now you can see that actually uh, there is no x and y that can satisfy all the three equations, right? There is no common intersection point for the three. So in reality, this has no solution. There is no solution to x and y such that we get we can satisfy all the three equations, right? So we can also put this into a matrix form, and this is how it looks like. So we can put a matrix for this, just multiply it with x comma y, and we have this vector that we want, right? So this is impossible. I mean, there is no value of x and y that can give you this vector over here, right? So what do we do? Is that the end? Can we do something better, right? So that these are the questions that one can ask. Can we do something about this, right? So one answer is approximate. What if we can approximate uh, this vector? Okay, so by approximate, what we mean is, can we find a solution that is the best approximate to what is required? We cannot get the exact solution, but can we have a solution which is very close to the original solution? So can we have a solution B which is very close to this vector, right? We need B which is very close to this. Now what does close mean over here, right? This is a very important question, because if it would have been just a number, a scalar, so we could say, okay, if you are not getting say 2.1, so what you can do is you can round it off to 2, right? This is what we mean by closeness, right? So 2.1 is close to 2. So but this makes sense when you just have a number, because you know which is greater, which is smaller in this case, right? But with vectors, what do? You cannot say whether a certain vector, say, I don't know, 2 comma 0 comma say -1. I mean, how do I call this vector close to this vector? So there has to be something that measures the closeness between two vectors, or in other words, we can say measures the distance between two vectors, right? So for that, we need a metric space. So metric space basically gives is a space where you can measure distances between two vectors. So that is the motivation to metric space, right? So let's see the formal definition. So for the formal definition, we have a tuple x comma d, where x is a set. Now x can be any set, need not be a vector space. So x is a set and d is a function defined as follows. So d goes from x cross x, that is the Cartesian product of x. If you are not sure what is the Cartesian product, I'll tell you now. And that gives you a real number. Okay, so the input is basically two vectors and the output is a real number, right? So let's take an example. So say my example x set is having these three elements. Okay, so this is x is a set which has three elements. So x cross x is basically ordered pairs of the set x. So we can take any two pairs, so 1 comma 2 and 1 comma 3. So 1 comma 2 1 comma 2 is itself a pair, right? So and then 1 comma 2 1 comma 3, and like this we have pairs, we have made pairs out of the x, right? And then this pair is given to the function d, right? So we wanted that, right? We need two things and we want to measure how close they are. So this is given to d. D is our function. You give any one of these ordered pairs to d, and what you get as an output is a real number, right? Quite simple, right? But there are certain conditions that D has to satisfy. So the first condition is, because this is in some sense the distance, right? So the distance between two vectors. So the distance between two vectors should be 0 only if the two vectors are the same. That makes sense, right? I mean, I cannot have two different vectors x and y. Suppose this is x and this is y. I cannot have some finite distance between them. Sorry, I cannot have zero distance between them if they are at two different places, right? There has to be certain distance. So only if the two are overlapping on each other, that is two are the same point, only then we can have a distance 0. So this is bijunction, right? I mean, if the x is equal to y, then distance of x comma y should be 0, and if distance of x comma y is 0, then x should be equal to y, right? So this is the first condition of this function. So now this function is yet not defined. You can use any function in the world that has this property uh, and some more to define it as a distance function, right? So this is the first property. It should follow this property. The second property is distance of x comma y should be equal to distance of y comma x. So that's also quite intuitive, right? X to y, this distance should be equal to y to x, right? It should not be that x to y is 5 and y to x is 4. That does not make sense, right? The distance should be same. The other property is, this is also known as the triangle inequality. So this is I mean, this is quite simple. I mean, if you, so what this says is distance between x to y. So okay, so let's take this. So there is this x to y, so this distance should always be smaller or equal to distance if there is some other z over here. So if I go from x to z and then from z to y, right? So this distance should always be bigger, which makes sense, right? I mean, if you are going a longer route, so this is a longer route, right? This is the shortest path. So this should be the shortest and then this should be longer, right? If you go through something else. So this is also known as the triangle inequality, because this forms a triangle, and what the triangle inequality says is that the sum or the addition of two sides of a triangle should always be greater than the third side, right? So these three conditions should be satisfied, and any function that satisfy these three properties can be our distance function D. Okay, so let us see some examples of the distance function. So the first is quite simple. Say x is a set of real numbers. So you take all the real numbers which can look like this. So we have a set of real numbers. Then you can define a distance function, distance of x comma y, as just modulus of x minus y, right? So if you want to say what is the distance between 1 and 3, so that is just 3 minus 1, that is 2. So 1 and 3 are two distances apart, right? And there's a modulus, so you can also do 1 minus 3 and then the sign is always positive, right? So that is a simple distance measure for r, and this is actually what we do, right? So when I gave you the example 2.1 and 2 in the start of the video, and I told that these two are close to each other, so these two are close to each other because when you subtract both of them, you get a sum of you get a subtraction of 0.1, which is very small, right? So if this distance is small, that means they are close to each other, right? If the distance is big, so like 10 and I don't know, say 100, so this distance is big, right? There is a distance of 90 over here, so then this is far away, right? So we actually know about this. The other thing is the Euclidean distance. We also know about this distance. I mean, you would have seen this distance as well. So this is nothing but the subtraction and then squaring them. So what this actually means is, say you have x, which is a 2, you are in R2. Okay, so now say your x is R2, so set of all vectors that are in R2, right? So here you can see x has x1 x2, that's the x coordinate and the y coordinate, and y has y1 y2. right? So okay, so just to make you clear, so over here this is x1 distance and this is x2. Okay, so that is how I have just numbered these things. And then over here this is y1 here and this is y2, right? So what does Euclidean distance says is, it says okay, do x1 minus y1, so that is xi minus y, and that you square, and then do x2 minus y2 and square that, right? So basically it is like this. Okay, so here there is a typo, so this is x2 minus y2. Okay, so x2 minus y2, and then you square that, and then there is x1 minus y1. Okay. This is 1, and then there is x1 minus y1, and then you square that. So actually the Euclidean distance is the shortest path, that is this. By Pythagoras theorem, you know that if there is this square plus this square, you get the hypotenuse, right? So the Euclidean distance is basically this, the shortest part between the two vectors x comma y, right? So we are actually familiar with this. Now this is also known as d2 distance. Okay, why d2? This 2 actually corresponds to the square over here. Okay, so when there is 1, so you can see there is no square over here, right? So actually in some sense there is a modulus over here, but because there is a square sitting over here, it does not matter, right? So this is the original Euclidean distance. Then there is something that is known as the d1 distance, where you don't square it, you just take the mod and you add them, right? So in this case this looks something like this. So you do x1 minus y1, this distance you add it to x2 minus y2, right? So this is, in some sense, this will only go either in this direction or in this direction, either in horizontal or vertical direction, right? So if you are familiar with chess, so this is what a rook does, right? So we have I don't know if I can draw it properly. So a rook looks something like this, right? So a rook either goes in the vertical direction or in the horizontal direction. So this is the distance that it will have to travel if you are in the d1 space, and you cannot go diagonally, right? So you can only go like this and like this. So this is how we define the d1 space. Okay, so you can see there is so much difference between the two spaces. When you are in d2 metric space, you can go diagonal. So you can see this is a shorter path. So d2 distance will be shorter than d1 distance, right? That makes sense, right? So say this distance is suppose 5, this is 3, and this is 4. Okay, so 5 is actually greater than 3 plus 4, right? That is 7. So d1 distance is greater than d2 distance. Okay, so this is something that actually changes the notion of distances, right? So that's what I want to say. Okay, now what is the unit distance in all directions? So by this what I mean is, suppose you are in the center, suppose you are in the origin, okay, and you want to see what is the unit distance. Okay, so for the axis it'll be, this is one distance, right? I mean, if, right, so this is 1, right? Over here you have 1 comma 0, right? This is 1 comma 0. So this is unit distance apart from this. You can put that into this formula where this yi, say it is 0, so this just goes away, so it is just xi square, right? So it is 1 square is 1. So this is 1 unit apart. Similarly, this, that is 0 comma 1, is again 1 unit apart. And the same can be called the same can be told over here, right, for these two, because they are just minus and there is this square sitting over here, right? So if you see for the Euclidean space, we are very familiar that if you have a unit distance all in all direction, then it will look like a circle, right? So all the points over here are of unit distance from the center. All the points have a unit distance, right? But what will happen if you use a d1 distance? So you see over here things change. So over here you will get a square like this. Why? Because you are just adding. So if there is a point over here that is half comma half, half comma half, this also has a distance of 1 from the center, because what is the d1 actually measuring? It is taking into consideration the horizontal and vertical distance. So to reach over here you cannot go diagonally for d1, you have to go either horizontal or vertical. So if you start with horizontal, you have to go over here till half distance and then go up till for another half distance, right? So that makes it 1. So all the points over here are unit distance apart for d1, right? So this is how this works. Similarly, can you imagine for d4 and d6, or d3, d4, d6, whatever, right? Can you imagine that? That is actually something interesting, right? Let me just make you visualize that. So one thing that you can see is that when you are over here, and also remember what is the 4 and 6 actually signify. So they signify the power over here. So this power is 2 because this is d2. This power is 1 because this is d1. So for a general case, for dn, say for dn, what will be the formula? So the formula will be something like this, say x comma y. So here, say 1 is at the origin. Okay, so this is say at the origin. So you just have uh, xi mod of xi, and then there is a n over here, right? And then there is a summation sitting. So if there is only 2, you are in R2, so there will be xi plus some yi, suppose. Okay, okay, let me not put yi, let me say x I. So basically what I want to say is that the two coordinates, right? And this yi is different. So over here you are considering this other point as the origin, right? So let me just quickly go to desmos and show you what happens. So this is our formula, okay, for an n distance, dn distance, right? So we know that for 2 it is a circle, right? For 1 we have seen that it is a square like this. So what happens when we increase n? So for n is equal to say 3, you can see that the circle is now getting elongated like this, and it is going approaching towards this square. So you can see, so as you move, you can see, right? So this, as you go further and further, this is approaching a square, right? So this is actually another distance. So when you get this square, you will get this square at infinity, because still at 100 you can see a curvature over here, right? So when this n reaches infinity, you will see a perfect square over here, and that is what is also known as a d infinity distance. Right? So that is the d infinity. And how do you write that in equation form? So it is like this. So it is the max of xi comma yi. Okay, so why that? Because you need the maximum deviation, because if there is a point over here, so this is 1 comma 1. Okay, 1 comma 1. So if there is a 1 comma 1 point over here, you need to put it in the same unit distance, right? This should also be a distance 1 apart. So you just take max of 1 comma 1 and you'll get 1, and hence this is also inside the units distance. So for this you get something like this, you get a square. So all the points on this square are unit distance from the center, all the points, right? So this is also a very important. Now how will d infinity look as we have compared the others? So d infinity looks at the maximum distance. So if you have 2 points x and y over here, whichever is the longest, that is the distance for d infinity, right? So in our previous example we used 3 over here and 4 over here, and then there was 5 over here. So we see 4 is longer, and hence this the d infinity distance is 4. So you can see for d infinity we got 4, for d2 we got 5, right, and for d1 we got 7. So you can see as and when this increases, your distance actually reduces. So d1 is actually the largest because you have to travel the largest. D1 is you have to go from here to here. That is your d1, right? For d2 it is the shortest distance between the two, and for d infinity what will happen is you have to see which is maximum and you just travel that much, right? So for d infinity it is just this distance, right? So that is how d infinity works. So these are some examples of the distance that you can use as a metric space. So let us stop over here. So here we have been introduced to the metric spaces. In the next video, we will see some more applications of the metric spaces, namely the convergence. So how can we uh, use the convergence? How can we use metric space to prove that some series is converging or not? That will be the next video. So that's all for now. I hope you have learned something from this video, and that's all. Thank you so much for watching. Thank you.